Good afternoon. I would like to introduce myself. My name is Keith Sloan. I'm one of the two main developers for the FreeCAD GDML Workbench, which I'd like to talk to you about today. But before I do that, I would like to thank the organisers of this conference with its very laudable aims of developing engineering skills, enhanced safety standards, and infrastructure that will remain safe and fit for purpose. I think FreeCAD's engineering-related workbenches also have a lot of potential to enable sustainable development. I hope and am sure the conference will be a great success and kickstart a great future for FreeCAD in such an environment. Let me introduce the main areas I wish to discuss in brief. Monte Carlo simulations, definition of the required geometry for the simulation, introduce the GDML workbench, cover some of its important facilities, mention some of the users we know about. Monte Carlo simulations are simulation of the passage of particle through matter. Such simulations are applicable in high-energy physics, nuclear and accelerator physics, the design of shielding in the space environment, various medical usages such as dosage, design of PET scanners, etc. The main related software is Geom4 and Root. Experiments are written in C++, but optionally you can have the geometry defined in a markup language, which is what GDML is. Monte Carlo simulation software has to consider particles passing through every surface, which favours defining objects as solid graphics rather than BREP shapes, and the use of sketches as used by modern CAD systems. One can create tessellated objects from these, but these often have large number of facets which have implications on simulation times. Looking at the GDML geometry definition, you have a defined section which defines various constants, position and rotations. You have materials which are quite different from FreeCAD's materials. These materials are defined in terms of their atomic properties. Solids, which I will talk about in the following slide. You have volumes. A volume defines one solid and one material and has an optional number of physical volumes. The physical volumes define the position and rotation. So you could have a volume with 4 physical volumes, and that volume would appear in 4 different locations. Assemblies are multiple volumes. There's various rules, no overlapping volumes, no duplicate names, etc. Now looking at GDML solids, there are over 30 solid types. FreeCAD's part workbench just has 6. Constructive solid geometry, those are things like box, tube, cones, etc., and make up the majority of that 30. There are some CSG-like, such as polygon and polyhedra. In the case of the workbench, these are all implemented using FreeCAD's part feature Python objects, and the objects' properties are the same as the GDML definition. So you can change the property through the properties editor, and things are instantly changed in the display. Some GDML workbench history. There was a meeting back at Slack in 2011, and Emmanuel Deluge, who was working at CERN, started a C++ workbench. Emmanuel seemed to stop working on his workbench. I started an initial FreeCAD workbench which was based on GM4's Python library, which at the time was still under development. That GitHub is still available, but it's been retired and archived. I then decided to take a new approach and implement a GDML workbench where the GDML solids were implemented as FreeCAD Python objects, so I could implement all the solids and have their properties as per the GDML definitions. Thanks to some recent enhancements by Mantha Hindi, this now supports arrays, mirrors, extruded and revolved sketches. It's useful to understand the relationship between how things are defined in GM4 and GDML and how things are implemented in the workbench. You have materials in GDML and also in the Workbench. Volumes in GDML are implemented as parts in the Workbench, and parts are also implement assemblies. The solids are implemented as GDML objects, and a solid can have a material. Note that with parts there is a placement, which is basically position and rotation in FreeCAD terms, and the GDML object can also have a placement, which is position and rotation. When you go to export, then the export sorts out the requirement for physical volumes and adjusts the placements to make the right physical volumes with position and rotation. So what you see in FreeCAD should also be what you see when you import the geometry into Geons. To create your GDML geometry, you first have to set up the GDML environment within the Workbench. You do this by activating the GDML Workbench and then opening a new file. This will bring in a whole load of GDML definitions, and you should end up with a screen that looks like the screenshot on this foil. You can then optionally import any XML file for any user-defined materials that you want added to this particular environment. You can then start creating volumes and assemblies by creating a FreeCAD part, and then you can add solids to each of those, adjust any properties, set the material, etc. Once you are happy with your model, then to export you select the base part, which in this case is world volume, and click File Export in FreeCAD, select GDML as a file type, and then that will export the file, your definition as a GDML file. I would like to briefly talk about the commands and icons that are available via the Workbench. There is a group of commands and icons that I would basically classify as utility. One of them involves setting the material and various things to do with the support of optical. The main group of icons are what I would consider the creation of solids. So there are 8 GUI GDML solids available via the Workbench out of the 30 that are actually 30 plus that are implemented. You can create one of these by just clicking on the icon. That will create a FreeCAD part, which is the volume, and then a solid, appropriate solid within that part. You can also create a part or what would be an assembly by using the FreeCAD part icon, which is the yellow boxy type icon in the set. There are also a set of icons to do with creating sketches and then using those to create GDML objects. It's like extrusion, revolving, mirroring, not to do with sketches, but arrays and scaling. There is also a set of icons to do with Boolean operations, so if you want to make unions, intersections, or joining together. And then finally there is a set of icons related to tessellating things, so either tessellating a FreeCAD object and creating a GDML tessellation, decimating such things, i.e. reducing the complexity of the tessellation, taking a FreeCAD object and making a mesh. Then you can use it makes available the mesh toolkit, and then you can convert that mesh back into a GDML tessellation, etc. Modern CAD systems involve creating objects from sketches. I'm particularly proud of a facility that we introduced in the GDML Workbench for creating GDML solids from sketches. We have Mantha to thank for this, for taking the initial design concept and implementing it. What actually gets exported is a series of Boolean operations on a number of GDML solids. This is an example of a revolved sketch. It is based on a step file, and I apologize now for not pronouncing his name correctly, that Federico Carminati wanted to convert into a GDML object. At the time, he did manage to produce a GDML tessellated object using the Workbench, but it was not without its problems. The end result was a tessellated object with 1,786 facets. Using a sketch and a revolved sketch to produce that object now would just mean a single tube and a generic polygon and then various other bits for the base. This is another example of the use of extruded sketches. What you have here is an imported step file, and using the 2-sketch add-on workbench, 3 sketches have been created at various cross sections. These have then been extruded, and then the extrusions have been fused together in Boolean, and that's created the final object. Munther, with a lot of experience of GM4 from his time at Lockheed Martin, realized that implementing arrays of GDML objects would be an extremely useful facility, and this is what he has done. They're exported as a multi-union, which means they're that much more efficient. The Workbench offers a number of facilities for creating GDML tessellated solids, either directly from FreeCAD objects or from meshes, and also manipulating those tessellations. One of the tessellation facilities is called GMeshMin. This first of all creates a mesh from the object and then uses GMesh recombine to reduce the number of facets. It does this by combining suitable triangular facets with cog facets. The screenshot shows Federico's step file, which has been GMeshMinned. This produces 1,799 facets and 1623 vertices. This is very similar to the result he obtained by using numerous processes in the Workbench in the past. When creating a geometry, there are a number of modes of working. There is the option of creating GDML solids directly. There's the option of using FreeCAD sketches, which you can then extrude and revolve. You can also design things in part design and then tessellate them, and you would then set the material. Or you could import a step file and allocate materials and tessellate that. Optical support. We did have a request to add optical support, which we have done, but it does involve creating a couple of external XML files. You put your matrix definitions in an XML file, and when you import that file, it will create spreadsheets within the optical section of the model. You have to do similar thing for the surfaces. You create an external XML file with the surface definitions and then import those. Having imported the XML files, you can then use the Workbench facilities to set a skin surface or a border surface for any of the volumes within the design. I'd just like to say a couple of things about import and export. If you import an XML file, then its definitions are added to the current design. You can do this for materials, a combination of a volume and a solid. You can also export XML. So for example, if you select the materials group, then file, export, and XML as a file type, then it will create an XML file with just those materials in it. You can then use that file within a different design. Exporting GDML, you can do that by selecting a world volume or an individual volume, then file, export, and choosing GDML as the file type. Other information. We're moving towards having installation work information in the README and usage in the wiki. Users. The GitHub repository has about 22 stars, and 8 or 10 users regularly clone after we do updates. We have 1 citation, thanks Lou Hillary, and we would like more. So if you use the Workbench in your research, then please consider adding a citation. As users, we have researchers in the GM4 collaboration and also Harvard Medical. We are aware of a number of PhDs and master students who've also used the Workbench. Thanks. Many people have contributed to the Workbench and we couldn't have done it without their help. I'd particularly like to thank Mantha, who has now become a major developer and made a lot of contributions in the last year or so. Future. We'd like to attract some youth so that Mantha and I can do some mentoring. We'd like to add command line scripts, user-defined materials, add more solids that can be created by the GUI, and check for overlapping solids, plus various other enhancements. In summary, the GDML Workbench can be used to create geometries for import into GM4 and Root. The Workbench does this by allowing the construction of CSG objects, where CSG is constructive solid graphics, the use of such objects along with FreeCAD's array, mirror and point cloud, the use of sketches which can then be exported or evolved, and these end up as exported booleans of CSGs, plus various facilities to enable tessellation of objects to create GDML tessellated objects. Thank you for listening to this presentation.